Hello everyone. Please note that this is a NotebookLM video presentation. Thank you NotebookLM. Hope you find it useful.
All right, let's talk about something really cool. We can teach a computer to tell a cat from a dog, but what about teaching it to, say, follow a recipe, to actually reason through steps? Now imagine you could teach it to skip the recipe entirely and just know what the finished cake is supposed to look like. We're talking about a massive leap in how AI thinks, from just following the path to instantly knowing the destination. And that really is the central question, isn't it? How do you teach an AI to execute an algorithm? I mean, algorithms are the bedrock of, well, everything, from sorting your emails to finding the quickest way to the grocery store. But getting a neural network, which is built to learn from fuzzy, messy data, to perfectly follow one of these super precise step-by-step procedures, that's a huge challenge. So there's this whole field dedicated to this problem, and it's called neural algorithmic reasoning, or NAR for short. The big idea is to use these incredibly powerful models, like graph neural networks, to basically create little neural clones of classical algorithms. The goal is to get them to handle these complex, multi-step jobs all on their own. Now, here's the problem NAR is trying to solve. Classical algorithms have what's known as the scalar bottleneck. Think about it like this. For a self-driving car, a classic algorithm might need a programmer to boil down the idea of danger into a single number. But with NAR, we can smash that bottleneck. It lets the AI look directly at the raw camera feed, all the messy, high-dimensional, real-world data, and figure out for itself what's dangerous. Okay, so how did we used to do this? Well, the traditional way was pretty brute force. We'd literally force the AI to mimic every single step of an algorithm. The network would process some data, then take its own output and process it again and again and again, painstakingly recreating every single stage of the calculation. It really is the perfect analogy. It's like making a student show their work for every tiny little line of a math problem. And, for learning, that can be useful. But you can probably guess it's not the most efficient way to get to the final answer, especially if an algorithm has like hundreds or thousands of steps. It's just slow. And this right here is that long, winding road in action. This process is called GNN on roll, and it literally forces the AI to follow that exact algorithmic trajectory, one laborious step at a time, all the way from the start of the problem to the very end. This is the question that changes everything. Seriously, what if the AI didn't need to show its work? What if it could develop something like an intuition for the destination? What if instead of walking that long, winding path, it could just teleport straight to the solution? And the secret to this teleportation lies in a powerful idea called equilibrium. The huge insight here is that for a lot of these algorithms, the final answer isn't just another step. It's a stable state. It's a point of balance where the answer just settles. So what exactly is equilibrium? Well, think about a GPS finding the shortest route. Once it's found the absolute shortest path, running the algorithm again isn't going to find a shorter one, right? The solution is stable. It's locked in. That stable state, where the answer just stops changing, that is the equilibrium. It is the final answer. And here you can see the difference so clearly. Instead of tracing that long orange path, step by step, this new model learns to find a direct route, a shortcut, a green line straight to that final, stable equilibrium state. It's not about mimicking the journey anymore, it's about knowing the destination from the start. And listen, this isn't just some clever programming hack. This whole idea is grounded in some really deep mathematical theory. It proves that for any algorithm that actually has an endpoint, a stable final solution, what mathematicians call a fixed point, is guaranteed to exist. So the challenge isn't proving it's there, it's teaching the AI how to find it. This new way of thinking has given birth to a whole new class of models, DEARs, which stands for Deep Equilibrium Algorithmic Reasoners. These guys are built from the ground up, not to follow steps, but to solve for that final equilibrium point directly. Now, the researchers behind DEARs make some pretty bold claims. They say this method actually improves performance and, maybe more importantly, is a huge step toward making these reasoning models way, way faster. So, you know what? Let's check the receipts. And the proof is right here in the training process. You can literally see the difference. On the left, A standard model's progress is all choppy and unstable. It kind of struggles to figure out what it's doing. But the deer model on the right? Look at that. It converges smoothly, stably, and reliably. This isn't just a cleaner graph. It means the model is learning in a much more predictable and efficient way. Okay, so it's more stable, but is it more accurate? Oh yeah, across the board, deers outperform the old models. But look at insertion sort. The old way got it right about 34% of the time. The deer model, almost 87%. That is a colossal leap. And even that overall 5% jump might not sound like a ton, but trust me, in this field, that is a really significant improvement. Look, better accuracy and stability are fantastic. They really are. But the most mind-blowing impact of this jump to the end approach, the real showstopper, is something else entirely. Pure, unadulterated speed. And here is the payoff. Just look at these numbers. The improvements are absolutely staggering. Depth-first search runs over 5 times faster. Strongly connected components, that's almost 16 times faster. And insertion sort, get this, is an incredible 21.8 times faster. These are not small tweaks, people. This is a fundamental breakthrough in efficiency. So you've got to be asking, how is that even possible? Well, it's because the model is no longer chained to that slow, one-step-at-a-time logic of the original algorithm. Instead of thinking like a line of dominoes, where one has to fall before the next one can go, it learns to see the whole problem at once and solve it in a much more parallel and direct way. So let's just boil this all down. What's the takeaway here? We have a model that is way more stable and reliable to train. It's step agnostic, meaning it doesn't even care how many steps the original algorithm took. It's more accurate, and it's dramatically, almost unbelievably faster. But the most important thing is that this is a foundational shift in how we can teach AI to reason. And really, that's the bottom line. This isn't just about some clever new architecture. It's a change in philosophy. It's about shifting from teaching machines to just imitate a process, to teaching them how to actually intuit a solution. And that leaves us with a pretty tantalizing question for the future, doesn't it? If an AI can learn to leap directly to a solution instead of having to trudge through all the steps, what incredibly complex problems, the ones that were once just impossibly slow to solve, are now suddenly within our reach?